Hi, this is a video editorial for the LeetCode Biweekly Contest 180. I'd say like this contest was on the easier end, so this editorial is going to be really short as well. Like Q1 to Q3 were like straightforward and trivial, and Q4 also has a because of the constraints provided, it has a really simple solution. So Q1, I don't honestly think this requires a discussion, but basically you just had to implement what the problem stated. Like if the timer is 0, you return green, else orange, and else red or invalid or whatever. So yeah, this was a straightforward implementation problem. Like the only scope of errors here is due to typos or something, I'd say. Q2 was straightforward as well. Basically, we are given an integer array nums which has some elements which are less than equal to 1e6, and we are given a digit which is 0 to 9, obviously. And we had to count the number of times any digit appears in all of the elements. So like obviously there are many ways to do this. During the contest I wanted to implement it really fast, so my idea was I can just maintain a frequency array and calculate the frequency of every digit and then just add it. And since this is 10 size frequency array, it's constant space, and this part makes the implementation really quick as well. So I think I implemented this in less than 30 seconds. But yeah, okay, so this was Q2. Q1 and Q2 were really trivial. Q3 was on the easier end as well this time. Basically, we are given an array nums and we have to make it alternating prime, and alternating prime means that the elements at even indices are primes and the elements at odd indices are non-primes. One is unique, so one would be a non-prime according to the problem statement. But yeah, and the operation we could do is increment every element by 1, and we have to find the minimum number of steps. So here my idea was like if element is like at an even index, we need to make it prime, right? So we had to find the nearest prime which is just greater than equal to it. Similarly, for odd indices we have to find the nearest prime which is just greater than equal to it. So I pre-calculated the primes and non-primes less than equal to 2e5 using a sieve. The sieve is n of log n, which can be pre-calculated since it's less than equal to 1e5. And then if the index was odd, then I was binary searching on the non-primes array, else I was binary searching on the primes array, and just adding that found element minus the current element to the answer. So this was Q3. Q4 was on the easier end as well. Basically, the problem stated that we have an array of binary strings, and the binary strings are represented by nums1i and nums0i, which basically means we will have one second, we will have nums1i ones first. Let's for some nums 1i equal to x and some 0 num0i equal to y. This means that we will have x ones, this is x, and then we will have y zeros, right? And what we had to do was we could rearrange this array in any way possible, and we had to make sure that the resulting number is the largest possible number, and of course since the number can be very large, we have to return the answer modulo 1 plus 7. And the constraints here like made this problem really easy. N is less than equal to 1e5, and the sums of all elements in nums1 and num0 is also less than equal to 2e5, which means that if we summed all, if we did this sigma num, what am I writing, one sec, sigma nums 0i plus nums 1i, if we did this, then that would be less than equal to 2e5, which means if we actually create a string by converting the implicit commands into an explicit string, that string's length will be less than equal to 2e5. So because of this observation, you can basically use the idea that like assume we have two strings, let a and b, and we had to create a number which is large by concatenating the strings. So we can concatenate a plus b, and then we can concatenate b plus a, and whichever is larger we return that, right? This is also like it's a common problem. So I did this only. I first of all converted this into the strings. I converted them into expressive strings. Then I ran this comparison thing to arrange the strings such that I have the largest number first and the smallest number at the end, and then I iterated creating the number. So the reason I didn't think of any DP or some idea here, because like the problem asks us to maximize a number and then it also asks us to do a modulo. Now if you are aware, the maximization operation is basically inequality, right? And if we do modulo, the inequality becomes void. So this gave me a really proper hint that the modulo is kind of pointless. We will have to do it at the end only. So this means that the our operation is irrelevant with the modulo. So we can do our operation first and then just do a running sum for the modulo. So this was my contest implementation. Basically you create the expressive strings here, then you sort them according to the rule, like if SL plus R is better, then put L first, else put R, and then this is just getting the number. Now of course this won't work if this constraint wasn't there. So if you wanted to solve this problem and this constraint wasn't there, we can do this. This idea is also simple. The main idea here is, first of all, now we can't explicitly form the string, right? So we have to use some observations here. The first observation is, like, assume we have one string like this and one other string like this. Obviously after concatenating them, their lengths will be equal, right? So we don't compare the sum of the lengths, but if one string has more ones at the front and the other string has less ones, so we can see after concatenating these two, one possible string will be this is this, and the other possible string will be, and then 1 1 1, right? So the string which has more ones is ideal to be placed at first, because then we'll have more values, right? Like here this will be some 2 power k minus 1 and so on. But the one with less ones will have a contribution of 0, which will mean that the number is smaller, which we don't want. So yeah, one idea was this. Now if the number of ones are the same, then we will compare with the number of zeros, and here lesser number of zeros would be better, because then the same idea will be here. So here if we concatenate them, we have this case, and in the other way around we have this case. So here, because of the lesser number of ones, we have the one appearing earlier, right? So yeah, this was my idea. We can sort it like this. And another case to handle here is if any number has no ones, like let's say this, no zeros. One second. Yeah, this is basically doing if a number has more than 0 zeros. One second, I'll have to clear this. I'll explain that case afterwards. So like once we have sorted it, this was my idea of, like, if the value of this was even larger, like let's say it was 10 power 18 or something, then instead of pre-calculating the 2 powers, we can use binary exponentiation, but that is not required here. So assume we are creating a number. Currently we have some x, let's say this is 0, and we have this block which we want to place here, right? It will be this one. So first of all, what we would do is we would want to shift the current number left by this much, which is 2 power the number of digits here. 2 power, let's say it has sz digits, so we will do this. Now after that we want this ones block, so we know the count of ones. We can just do 2 power ones count and then minus 1 to get this block, and then we will again shift this by this amount, which is the number of zeros. So this is what I'm doing here. I'm first of all shifting the entire thing left, then I'm getting the ones block, and then I'm shifting it right by the number of zeros, and then I'm adding it to this, obviously. Now here one edge case to notice here is, while sorting, what can happen is, one second. Yeah, this here while sorting, what I'm saying is, if any block has 0 ones, we were given this additional constraint that nums 1i plus nums 0i is greater than 0, which means both cannot be 0. So if a block has 0 zeros, that means it will have all ones, right? And if a block has all ones, it is always better to put it at the first. So like assume we had a block with 1 1 and 0 zeros, and we had a block with, let's say, 10 ones, like 4 ones and 1 0. In this case, putting this at first will objectively be better, because like if we did the other way around, this 0 will kill this thing, right? It will become here and it will drop the value. So this was basically the sorting idea here. Yeah, these were the solutions I implemented. Like during the contest I would have implemented this, but since this constraint was fairly obvious, so I just did the easy solution instead. Now right after this I'll be attaching the live solve section where you can see how I approach these problems live. Alright, bye.